Okay, welcome. Hi, yo, sup. Today we're talking more about complex numbers. So last time we talked about the magnitude of a complex number, the idea of a complex number, the conjugate of a complex number, and so on and so forth. This time we're going to be talking about some other stuff. So, before I get into those, I want to talk about some formulas, or not formulas, but how to manipulate some of what we know to get more of what we know. For example, I want you to try. Oh my God, what's happening? I want you to try something for me. I want you to get out some scratch paper or something and try to do z times the conjugate of z. What's that equal to? Okay, I attempt you've tried it now. So we have a plus bi times a minus bi, and we've already done this, but it's just a review. That's just a squared plus b squared, right? We know this. But we also know that the magnitude of z is equal to the square root of a squared plus b squared. This means that z times this is equal to the magnitude of z squared. That is kind of important, if you ask me. Cool, right? Nice. So now we're going to be talking about more about these kind of things. Like, you can use some of what you know to get some more of what you know. Let's look. So, yeah. So now I want you to try to see. So let's say we had a complex plan. I'm not going to draw it nice and neat, but this is z. Where does negative z fall? Where does the conjugate of z fall? And where does the negative conjugate of z fall? Okay, so this is where z is. This is a plus bi. Negative z, that's just gonna be negative a minus bi. So we go, instead of a, we go negative a, and we do minus bi. So that goes here. It's symmetric about the origin. Okay, done with that. Where does it's like a diagonal kind of like symmetry. So now where does the conjugate of z fall? Well, this is going to be a minus bi. So a stays the same. It stays here, but instead of plus bi, we go minus bi. So this is where the conjugate. This is where negative z is. Now what about negative conjugate of z? Now that's going to be, so the conjugate of z is a minus bi. This is going to be negative a plus bi. So we go negative a, and we go plus bi still. This is the negative conjugate of z. This creates a rectangle. It's cool, right? Even draw that and draw these. So yeah, that's where they go on the plane. I just want you to get that idea in your head. If it stops lagging. Okay, now I want to introduce you to kind of like manipulating some of like the magnitudes and conjugates. So I want you to prove something that, actually I just want you to find something. What is the magnitude of z times w? Okay, let's say this is a plus bi, this is c plus di. We're gonna get the magnitude of a plus bi times c plus di. That's equal to the magnitude of ac minus bd plus bc plus, or I'm going to do ad plus bci. right? You can try to expand that out. The real parts is A times C, right? And then BI plus DI is minus BD, so that's the real part. And then the imaginary part is C times BI or BCI plus AD times I or A times DI, which is ADI. Factor out I, we get AD plus BCI. Now we can use our formula. So we have that is equal to the square root of AC minus BD squared plus AD plus BC squared. That will get us to the square root of A squared C squared minus 2ABCD plus B squared D squared plus A squared D squared plus 2ABCD plus B squared C squared. That is equal to the square root of that's equal to the square root of AC squared why don't this erase? Hold on. Anyways, yeah, so you have AC squared plus BT squared plus BD squared plus AD squared plus and then these cancel. So that's it. Now what you can do is you can factor something. So now you're gonna get the square root of, you can factor out a c squared at the first two. You get c squared times a squared plus b squared plus the factor of d squared times a squared plus b squared. Factor out of a squared plus b squared, you get a square root of a squared plus b squared times c squared plus d squared. Now we can split this square root into the square root of a squared plus b squared times the square root of c squared plus d squared. But now we know that's just the magnitude of z times the magnitude of w. Cool. Now I've probably by now forgot what I was looking for in the first place. I'm gonna go back up if this loads. Okay, so why don't this load? It takes so long just to load. God, this is so slow. Anytime. Okay, now it's doing too much. Okay, so now what we were looking for is this, and we got the answer of this. That's really helpful. And using kind of like induction, we know that this is just, if we add this, that's equal to this times, that's equal to this times this, and that's equal to this times this times this. Okay, so we can keep doing like that over and over to get our results. Now what I want to do is I'm going to square this. That's what I want to do. So now, I'm going to get more into the real and imaginary parts of z. So z is equal to a plus bi, right? Remember his real and imaginary axis. So our notation was like this, equals a, and imaginary part of z equals b. If you don't know this, that's how we write this. So now I want to prove. So now I want to prove to you that the real part of z equals z plus the conjugate of z over 2, and that the imaginary part of z equals z minus the conjugate of z over 2i over 2i. Why is this the case? Well, this is equal to a plus bi plus a minus bi over 2, which is equal to 2a over 2, which is equal to a. So this works out. Now this is equal to a plus bi minus a minus bi. Or, sorry, minus a plus bi. Right, this is minus a minus b. Okay, yeah, good. Over 2i. That's equal to 2bi over 2i. That's equal to b. So this is also true. You can also reverse engineer this to get the proof, right? So we look at a, and we say that that's 2a over 2, and then 2a, maybe if you're really weird and smart, you might notice that that's z plus the conjugate of z. Same for b. So now, I want to show you that, I want to use more. So maybe in pre-algebra or arithmetic, you might have learned that if there's z and w, or maybe not z and w, if there was a and b, then they're on the number line somewhere. Right, there's some points on it. So now, the distance between a and b is the absolute value of a minus b, or absolute value of b minus a. Right? That's the same case with complex numbers, but on a two-dimensional surface rather than a one-dimensional. So, on the plane, if there was z and there was w, the distance between them when you make a line is the magnitude, same notation as absolute value, of z minus w, or the magnitude of w minus t. I want to prove this to you, and it seems very intuitional that this is the case, and it is, but I just want to prove it to you algebraically. So let's say you have the magnitude of a plus bi minus c plus di, and we know that that's the same as w minus c, right? Because absolute value, just if it's negative, it just flips it, right? We know this. So so now this is just a minus c plus b minus di, and that is the square root of a squared minus 2ac plus c squared, that's a minus c whole squared, plus b minus d whole squared, which is b squared minus 2bc, 2bd plus d squared. That is equal to square root, or not, what we're trying to prove is that the magnitude of z minus w, we can create this triangle. This is z minus w, or this is a minus c, and this is b minus d, or d minus b. Wait, but we've already proved that. When you think about it, we don't need to do some ugly algebra and ugly cancellation stuff like that. This is a minus c whole squared, and this is b minus d whole squared, right? A minus c, a minus d. So we've already proven it. Okay, so now that we've proven that, I'd like to show to you that I want to go back to basics. So I want to prove something very simple. What is the conjugate of the conjugate of z? It's very intuitional. That is just a plus bi. That is just z. Now, why? Well, the conjugate of z, we first ignore this, and we first just do the conjugate of z. Or sorry, no, there's no line here. So we first do the conjugate of z, we get a minus bi. The conjugate of that is a plus bi, and that's equal to z. So that was a simple proof. I just wanted to show that to you. Now, I want to do some manipulation. So, first, actually, before I do some manipulation, I didn't really go through this last time and this time, but zw is equal to, or z times w, that are complex numbers, a plus bi times c plus di. That's equal to, I just wrote out what it is, equal to ac minus bd plus whatever, ac plus bdi or whatever. But if you expand this all out, you get ac plus adi plus bci plus bdi squared. That's equal to ac, and then this becomes -1, so this is just minus bd. So we get ac minus bd plus ad plus bc I. We can factor out an I, but we're gonna put it late at the end. So there you go. That's all I did. Okay. So now I wanna so sometimes you might know something, but you don't know another. So like, let's say you know the magnitude of something, and you're trying to do multiplication. You can't do the opposite magnitude or the inverse magnitude or whatever. So let's say you were trying to do, what is a w over z? We did this, right? Last time we made, it's kind of like rationalizing the denominator. We made the bottom a better number, a real number, and then we split it up into its usual format of a complex number. But I want you to notice something. This is w times the conjugate of z over z times the conjugate of z. That's equal to w times the conjugate of z over the magnitude of z squared. We can also do the same thing with w. That's also equal to, so we have this as one thing, and another thing is we can also have, from w over z, we can go to w times the conjugate of w over z times the conjugate of w, and that's equal to the magnitude of w squared over z times the magnitude of w. This is another. And these things are both equal. So we can say that w times that over equals And that means that if you use cross multiplication, we get z times the conjugate of z times w times the conjugate of w is equal to magnitude of z squared times the magnitude of w squared. Well, this is the magnitude of z squared, and this is the magnitude of w squared. So we proved it and we checked it. That's good. That's another thing you should use sometimes. And remember, if you don't know something, you can always prove it. And go through the understanding of it or whatever. Another thing, or not another, but a few more things I want to show you before I end this is that I'm going to leave these all as an exercise for you because they're relatively simple to what we've already done. And they're just going deeper into what we've already used. So I want you guys to prove at home that the conjugate of z plus w equals the conjugate of z plus the conjugate of w. I also want you to prove that z, or the same thing, the conjugate of zw equals the conjugate of z times the conjugate of w. Also, I want you to prove that that z, or we already did that, I think. Wait, did we do that? I think we proved this, right? If we didn't prove it, I think we did though. So we're all good. But if you didn't, do prove it. I also want you to prove that did we also prove that? Yeah, we did. Okay. So that's all I want you to prove at home, and just know it's true also. And I'll see you guys next time. Goodbye. Also, oh yeah, one more thing. 1 over z is equal to z times z over, or z, the magnitude of z over squared. Okay. Okay. Goodbye. Thanks for watching.